And I'm not going to be really writing anything down here. I'm just going to go through, and you can add notes if you wish to. This unit deals with exponential and logarithmic functions and equations. To begin with, you need to recognize that this basic exponential function we're looking at here of y equals c to the x will have a y-intercept of 1, and it will have that shape if the base is greater than 1. This is what we call an increasing exponential function. So that word increasing is tied to the base being a number bigger than 1. There's lots I'm not going to review here, like the base must be a number that's positive. You cannot have negative bases, and you cannot have a 0 base, and you cannot have a base of 1. Okay? I feel as though, as the years go by and I teach this course more and more, I feel as though I shouldn't have to say this next part, that you need to be able to handle transformations of y equals 2 to the x, for example, by vertically stretching and horizontally stretching and vertically and horizontally reflecting and translating, because this was the first week of classes. We spent the first week of classes learning about a, b, h, and k. And every time we learn a new function, whether it's sine of x, or root of x, or log of x, you have to be able to apply that. So knowing the properties of this graph will allow you to find the properties of this graph. Obviously as well, everything else you're expected to do with graphs from whenever you first learned about graphs, you need to be able to do with these functions. What is the x-intercept? Not of this function, because there is no x-intercept, but if this function g of x, what is the x-intercept? Well, you would put 0 in for y and rearrange this for x. And by the way, you should be able to rearrange that for x, even though there's no numbers there. Okay. Decreasing exponential functions, however, are really horizontal reflections of increasing exponential functions. The thing that makes this a decreasing exponential function is the base is between 0 and 1. The y-intercept is still 1. And again, decreasing is indicated by the value of the base. And same thing, right? You need to know how to apply the transformations. Did I give you 2 of these? Okay. To that function. What's missing here, by the way, I don't quite know why I didn't put it in there. You need to know there's a horizontal asymptote on the x-axis, right? Okay. So, and this is what we talked about in class. I don't know that I've actually put this in your note package that you're looking at right now, but I know it's in your general Unit 5 package. Exponential growth and decay. So for exponential growth and decay, this thing which is on your formula sheet is what you use to solve any problems involving exponential growth or exponential decay. Declining value of an investment, increasing or growing value of an investment. Population growth, population decline, half-life. In this formula, and I'm highlighting here for you on the screen these 2 things first, because I think it's very important you understand they are the variables. They are the things that are changing. If we were to talk about a graph, y is on the vertical axis. It's the number of mice, and t is the time. Maybe it's the number of days on the horizontal axis. Everything else are parameters. These 3 things are parameters. Each individual application has a constant value for A, a constant value for B, and a constant value for P. For the assignment that's due on Monday, Gloria's problem is going to have a number for A, a number for B, and a number for P. Jay's is going to have another number for A, another number for B, and another number for P. A is the initial amount. B is the factor by which things are regularly changing, and that the word factor implies multiplication. So B is the number that you are multiplying the population or the money or whatever by regularly. If B is 2, something is being doubled regularly. P is how long it takes for that to happen. And I've got some specific examples that I'm going to go through here. So this is what the graph looks like. It could also look like that. By the way, both of these graphs we're looking on the next, I guess we're looking at the next page. Did I have one before? I didn't. Okay. Both of these y-intercepts, by the way, are A, the initial amount. I'm going to give you some examples here. If I told you there was radioactive decay happening and the half-life is 34 years, what that means is P, the length of time it takes the thing to happen, is 34 years. But you need to know for half-life that B is automatically 1/2 or 0.5. That's something that, look, if you're lucky and you're writing a diploma exam and you do see a question like this, maybe they tell you that's what half-life means. But they don't have to. If the population is growing by 4% every year, this is one of these ones that's just pretty obvious. Since it's every year, P is 1. And since it's growing by 4%, 4% added to 100% is 104%, which is 1.04. If a value of something, I don't know why this would happen. Okay, I don't know. Maybe it's an annuity that you have this big bulk of money in an account and every 6 months you're drawing out 12% to cover some expenses for a business or a scholarship fund, or I don't know. It doesn't matter. If it's declining by 12% every 6 months, then B is not, well, what's 100 minus 12? 88, right? B is not 0.88. Sorry, it is 0.88. I thought that was an annual thing. B is 0.88 because the decline of 12% means you're going from 100 to 12% less, which is 88%. Okay? And it's happening every 6 months. I would prefer, personally, not to use months. I would use 0.5 years. If it's 8% compounded quarterly, now listen, I didn't put 8% per year here, but it means 8% per year. Sometimes they don't say that. If a bank advertises 8% compounded quarterly, they really mean 2% every quarter. If it's 8% for the whole year, if I had $800 and I was going to give you the $800 over a year, but I gave it to you in 4 pieces every quarter, you'd get 200 and 200 and 200 and 200. Okay. As basic, and P is 0.25, and you need to know this for either Gloria or Jay's investment in your assignment, but as simple as this bottom idea is, people get this question wrong on an exam because they just see a percent and they see 12% and they go 1.12 and they don't think about it. All right, so again, this isn't in the package I gave you today, but this is something that's in your notes. When you have a base between 0 and 1, it's a decreasing function. And with regards to this equation, even though it's more complicated than a base raised to x, in regards to that equation, the base still tells you whether it's growth or decay, whether it's increasing or decreasing. Meaning of a logarithm, the inverse of an exponential function is a logarithmic function. So you're going to see in your review handout how I can ask these questions. But basically, these two functions here are inverses of each other. But rather than writing x equals 3 to the y, you should know, this should be easy. You should know x equals 3 to the y means log base 3 of x equals y. So these two things are the same. Right? This is the translation from one language to the other. But that means that these two things are the same. So I'm telling you y equals 3 to the x is the inverse of y equals log base 3 of x. And if you graph them, you need to be familiar with the graphs, which I'm going to run through right now with you. If the base is bigger than 1, this is what log base 2 of x, for example, looks like. When we did some problems a week or so ago, I said that in order for us to come up with what this looks like, you should start with y equals 2 to the x and find the inverse. I think we've graduated beyond that now. I don't think you have time on an exam to do that. You need to recognize this graph. You go up 1 and things get doubled horizontally because the base is 2. There is a vertical asymptote on the y-axis. Needless to say, you have to be able to explain transformations. So for example, you need to know that x equals h will be the vertical asymptote, because that's going to shift the whole graph left or right. And as well, you need to be able to use your skills to find x-intercepts or y-intercepts or any other features of the graph, because now you know how to work with logarithms and exponents. If the base is between 0 and 1, this is what the graph looks like. And you can make a note on your handout that I'm going to leave this in here the way it is, I think, yeah. But according to a bulletin that I got from the government today, not today, this year, they're saying that students are not expected to deal with transformations of this logarithmic function. I don't think it should really matter. And sometimes I don't always trust what Alberta education tells us, because then I get a diploma exam and I look at it and I go, wait a minute, you're not supposed to be able to do that, but it's on there anyway. Laws of logarithms, we're coming near the end here. These 3 laws of logarithms should be as familiar to you as the freckles on your face. You should be intimately familiar with these 3 things. I don't think, unless you're getting stressed out on an exam, you will need to look at your formula sheet to find them, but they're there in case that does happen, okay? What do we use these for? Well, man, you're going to see a boatload of different kinds of questions. You can combine logarithmic expressions. You'll see this in the review. You can solve equations that are exponential or logarithmic using these. You can solve just puzzle-like problems, and they get quite complicated. Remember, when you're dealing with logarithms, if you don't know what to do, rewrite them in a different form, either using these laws or the meaning of a logarithm. For product and quotient rules, there is a shortcut. Negative logarithms have an argument that gets put in the denominator of the entire argument for a single logarithm, and positive get put in the numerator. Whenever you apply these rules, the basis must be the same. Solving exponential equations. I haven't decided what's going to be on your exam, but this is a classic kind of written response question where I give you, and I may give you something different this year. Last year, or last semester, I think I gave a written response question, and one of the questions had an exponential equation where the bases could be written in the same base. 16 raised to the 2x plus 5 equals 8 raised to the 7x minus 2. And you can write 16 in base 2 and 8 in base 2 and solve it using a common base. Do not, my advice, do not make the mistake of thinking, well, I could use a common base, but I'm going to take the log of both sides anyway. That's a road you don't want to go down unless you have to. It's much simpler to just write them in common bases and set the exponents equal to each other and solve. If there is no common base, and this is the second part of that written response I had last time, here's an exponential equation, solve for x. You need to take the log of both sides so that you can move the exponents down like we've been working on the past couple days and solve. Solving logarithmic equations. There's 2 general things here. If you can simplify so that you have a single logarithm equals a single logarithm, then the arguments are equal. If you can't, but you can simplify it so you have a single logarithm equals a non-logarithm, then rewrite it in exponential form to solve. The final thing I'm going to show you here may be typed up a little bit differently than what's on your handout. Always check for extraneous roots, which are then discarded. Extraneous roots must fit into the domain of the argument being greater than 0. So if the argument is 4 plus x, then you have to figure out that 4 plus x is greater than 0, which means x is greater than negative 4. And that's it. I have a number of handouts. The first one I'm going to give you is the one that I've made up, which is a series of multiple choice numerical response questions based on what I've seen on diploma exams over the years. I've broken this one up, although your exam will not be in any kind of sequential order. I have broken this one up into different sections. So graphs of exponential functions comes first, then I think applications. There are other, well, I'll just say it this way. You know, of course, that the review problems typically start off with simpler kind of questions. And in fact, maybe the review sets don't even contain questions that you might see on an exam. What I'm getting at is you're going to see on your exam questions that may be unfamiliar to you, that you may not have seen before. That's part of us evaluating you in math at this level. Can you take what you've learned and apply it to a new situation? Okay. So I have that handout. I do have an additional handout here. If you are interested in having it, you can. This is just multiple choice questions. You've seen a similar handout like this for other units. There are 65 questions. In the back, there's an answer key, and there's also solutions, meaning it's showing you how to get the answer. Okay, so you can certainly, you usually want one, so I just thought I would hand it to you. You can certainly pick that up if you like. So get to work, please. We have about a half hour here, a little less than a half hour to get some practice today. Remember, the deeper you dig, the harder you try, the more work you do, the more you'll be rewarded, mark-wise, right?